Okay, so this is section 8.3, the converse of the Pythagorean theorem, objective 4. I have this as a warm-up. This is just algebra exercise, but this is actually coming from the 8.1 packet, the 45. This is the very last one that I excluded because this is a little too hard, but I wanted to show you. This is for the B. See, this is the same equation right here in your packet. To show algebraically that arithmetic mean between two different numbers, R and S, is greater than the geometric mean. So like if you take the regular average of two numbers, that is going to be bigger number than the geometric mean of these two numbers. And then you are trying to prove them. And this is how the geometric mean is expressed, right? The square root of the product of two numbers. And this is how arithmetic means are expressed, the sum of the two numbers divided by 2. So this is always greater than this. To prove this, these two numbers, the difference of two numbers squared, whether this number is either positive or negative, if you square them, as long as there's a difference in numbers, in two different numbers, so there have to be a difference. This number have to be greater than 0, right? So this is something that is universally accepted as a truth, and if you can go backwards to here, then you can prove that arithmetic mean is always greater than the geometric mean. But it says work backwards from, that's a hint, backwards from here to this, and then reverse the steps, because it's very hard to go from the simpler equation to the more complicated equation. So what it's saying is work from here to here, just like if this, then this, that would be algebraic proof. If this is true, then this is true. But we know already this is true. So once we do that, we reverse the step so that you start with this as accepted truth, and then therefore this is true. Okay? I'm not going to show the reversing the step part, but I'm going to show you how to go from this to this. Now, I want you to stop the video now and try yourself if you can get there. Okay, it's interesting. And then don't try too hard, just try a little bit and see, and then come back and then do it together. Okay, so assuming that you did that, here we are. So you know, inequality is, you can treat it like an equal, except that when you multiply or divide by a negative number, you have to flip it. That's the only difference. So in this case, you want to get rid of fractions, so you can multiply both sides by 2. R plus S is greater than 2 square root of RS. Okay, and then I want to get rid of these radicals, so you're going to square both sides. So you have R plus S squared is greater than, if you square this, this is going to be 4, and this is going to be RS, right? So 4RS. Okay, and you're going to FOIL this, so that's R squared plus 2RS plus S squared is greater than 4RS. Okay, now you're gonna move this over here. R squared minus 4RS plus 2RS is minus 2RS plus S squared greater than 0. I subtracted 4RS from both sides, so it's a 0, right? This, if you recall, this is R minus S squared is greater than 0. And that's what you got here. Okay? So if you see it like this, it's not hard. But coming up with this from here to here on your own, hopefully you tried it and then see how far you went there. So this is kind of algebraic proof. Okay? All right. So let's start with 8.3, objective 4, state and apply the converse of the Pythagorean theorem and related theorems about obtuse and acute triangles. Okay, so the converse part is pretty simple. The new idea is this obtuse and acute triangles. So that's the only thing I wanted to go over. Okay, so the Pythagorean theorem is that if ABC is right triangle, then hypotenuse square is the sum of the square of the two legs, right? The sum of the square of the two legs. That's the Pythagorean theorem. The converse is, if hypotenuse squared equal the sum of the square of the two legs, then triangle is the right triangle. Okay, and converse is true. And here is the step of proofs, but you can read them and understand them, but we're not going to go over this. Basically, if hypotenuse square equal the sum of the square of the two legs, then it is a right triangle. Okay, and knowing that these are very convenient numbers to memorize, these are called Pythagorean triples. Pythagorean triples. These are numbers that if you square and add them, you get to this. These are whole number that have that relationship. So 5 square plus 12 square equals 13 square, and so forth. And the multiple of these also works too. So 3, 4, 5 is the most famous one. So 6, 8, 10 would work, 9, 12, 15 would work, 12, 16, 20 would work, 15, 20, 25 would work, 5, 12, 13, 8, 15, 17, 7, 24, 25. I usually forget this one. I know this, and this. I forget this one. Sometimes I remember, but usually I forget this one, and I forget that it's a multiple. I do see these pretty easily, but I don't always see these. So it's just, if you see, identify it, you can speed up the process, because then you don't have to square it and add it and then take a square root to compare if they are the same. Okay. By the way, you remember the Fermat's last theorem is, so this is a square plus b square. This is a little bit of side note, but, and hopefully I have time to show you the video one day, the whole video. But so these are all whole numbers that satisfies this equation, right? So the Fermat's last theorem is that there is no whole number that satisfies this equation. The square is the last number you can do. Any number above 4, 5, 6, any number above, there is no whole number that satisfies this equation. And that's such a simple concept, and then it was so hard to prove. And American mathematician proved it in like 1989. That's a really fascinating story if you're interested. Okay. All right. So this is the new part right here. Okay. So this is the A3, the converse. So if this relationship holds, then that's a right triangle. If the hypotenuse square is shorter than the sum of the two legs, then it's acute triangle. It makes sense. It's not long enough, right? It's not long enough to be equal. So this have to be smaller. It's tighter, right? Not short enough. So it's acute. If the hypotenuse square is longer, so it's too long. It's 90 degrees. It's too long. So it's obtuse. Okay, so that's it. That's it. If these hypotenuse is shorter, then it's acute. Hypotenuse is longer, then that's obtuse. And then if you get confused which side it goes, just think about it. 90 degrees, too short, acute. Too long, obtuse. Okay, so triangle has the side lengths and acute, right, obtuse. So just to square them, and then always the longest one is the hypotenuse, which is the other side of the equal. These are the C's, right? So square this, add this, and then come up with whether these are acute or obtuse, okay? So you can do this one. And here's a practice. And my dog is asking again. Exercise. Okay. The triangle form. So triangle can be formed, say not possible. This is something that we were supposed to cover in chapter 6, but we didn't do that. But the idea is, for the triangle to be a triangle, this plus this have to be longer than this, right? Because if this side, let's say this is A, B, and C. A plus B is shorter than C. There is no way you can make an angle and then connect these points, right? So it's not possible to form a triangle when the sum of the two sides is shorter than one length. then that's not possible. So in any situation, some of the two sides should be longer than the third side. If the sum of the two sides is shorter than one of the lengths, then it's not going to be a triangle, right? You can't make a triangle with two sides that is sum is shorter than, because this is going to get absorbed in here, right? And it's not going to make a triangle. So that's the idea here. So do odds here, okay, and specify all values of x that make the statement true. Okay, so you have to find, if this is 90 degree, you have to find x value. This okay, so let's do this one. And triangle is isosceles, so you have to be either 8 or 6. No triangle is possible. Okay, so let's try this one and this one in the video, and then you do A, C, D as homework. Okay, so for this to be acute, this square have to be smaller than 8 square plus 6 square, right? It's too short. It's acute. So x square is smaller than 64 plus 36. So x square is smaller than 100. And then if you remember this, this is the multiple of 3, 4, 5, right? It's double. So instead of 5, it's a 10. So x is smaller than plus minus 10, but since we are talking about lengths, the minus doesn't matter, so it's a plus 10. So this would be the answer for B. Okay, and then no triangle is possible. The x have to be longer than the sum of the two numbers, which is, so this is H, E. So x have to be longer than 8 plus 6, so x have to be larger than 14. Okay, and you do the rest. And here's one more problem. Explain why x must equal 5. Interesting. Explain why angle D must be a right angle. Explain why angle P must be a right angle. Okay, I think you can do these, hopefully. Let's do 8 together, okay? All right, so this is 10, right? And 5 and 5, that's 10. And this is 8, and this is 6. So this is actually 5, 4, 3 Pythagorean triple. So that means that this square equal this square plus this square, right? If you want to do it, the 100 equal 64 plus 36, right? So that means this is right angle, right? If this is right angle and this is 5 and 5, so this is median. You remember the theorem that we did? The median drawn to the hypotenuse of right triangle is median is equidistant to the 3 vertices of the right triangle. And when we proved this, we did this, make it a rectangle, and diagonals are congruent and bisect each other. So these have to be the same length, you remember? So that's why x have to be 5, okay? And try those, and we do the rest in the class.